Hello physics students, this is Dr. Brinzy and this is lesson 7.1.1. We're going to be calculating the forces required to keep an object in equilibrium. Before I talk about what equilibrium is, or remind you what equilibrium is, I want to talk about a couple of topics that are important related to equilibrium, and that is the center of mass. We learned about center of mass in Unit 4 when we were talking about momentum. And this is the formula that we have for center of mass. So if you want to calculate where an object's center of mass is, we just add up all of the masses times their distance and then divide it by the sum of the masses. So if you say have if you have three objects connected by a massless rod, and you wanted to know where their center of mass is, you would need to know what each mass is, M1, M2, and M3, and then you'd also need to know what each distance is. So we would say that this is, if we're counting from the left here, we would say that x1 equals 0. Okay, and this would be x2, and then the distance all the way from where we started is x3. Okay. Now, there's also a term that is interchanged with center of mass a lot, and that's what's called center of gravity. And in almost every situation where you're going to run into this, really the center of gravity and the center of mass are located in the same place. So we would say xcg, which means center of gravity, equals xcm, which means center of mass. If you're curious about when they would technically be different, feel free to come talk to me at some point, and I'd be glad to explain to you. But I think for the purposes of this video, we're really not going to get a problem where we have to differentiate between those two. So we're just going to say center of gravity equals center of mass. Now, in order for an object to be in equilibrium, two facts have to be true. An object's in equilibrium if, number one, the net force on the object equals 0. So when we say net force, F net, what we are used to doing is we're used to adding up all the forces together. And instead of writing out F1 plus F2 plus F3 ... we actually just use what's called a summation symbol, which is this, it's actually in a capital letter sigma in real life. Let me see if I can rotate here so I can bring out my pointer. All right. Well, you guys don't see the rotation that we do. But anyway, this is a Greek letter capital sigma. And you just need to remember that it's a summation symbol, which means you're adding up all the forces together. Now, we have to keep each direction treated separately. So when we say that the sum of all the forces equals 0, we have to say the sum of all the forces in the x direction is equal to 0. And then separately, we have to keep an account of the forces in the y direction, which is up and down, as opposed to the x forces, which are left and right. So that fact has to be true in order for an object to be in equilibrium. Another thing that has to be true for an object to be in equilibrium is that the net torque on the object has to equal 0. And we calculate net torque by adding up all of the torques on the object. And if it's in equilibrium, then the sum of all those torques has to equal 0. Now we're going to run into a lot of problems where there is no pivot point defined where we can actually take a torque, because after all, torque, if you remember, is equal to R times force times sine of theta. Okay. In other words, we put this here because we are concerned about the force perpendicular to the radius. Now, torque requires us to know a distance r, and then you remember that distance r is from the pivot. So if this is my pivot, and I am applying, let's say this is my object, and let's say I am applying a force in this direction. Well, there is an angle theta between this force and my object. And this angle right here would be theta. Okay? This distance right here would be r. I'm applying it at a certain distance r from the pivot. We need to know that, but there are problems where you're not actually given a pivot point. Well, lucky you, because if there's no pivot point defined in the problem, you get to pick one. And sometimes picking one can actually make problems easier, especially when we're dealing with finding unknown forces in an object that's in equilibrium. And I'm going to, especially with the AP, go through an example of that. Right. Oh, I think I just, all right. I think I just, oh shoot, okay. I'm actually going to skip that part because I just kind of explained that to you. So I'm going to skip that. And we'll just go forward here. There's going to be a little stuff that's scribbled on there, but okay. Next slide. And let's go through an example here of how we would apply this equilibrium to a physics problem. So let's say we have a car that is parked. So when a car is parked, or when a car is in uniform motion, in other words, it's not accelerating, it doesn't have positive or negative acceleration, then we can say that that object's in equilibrium. So if we have a parked car, the parked car is in equilibrium. So let's say we have a car, it has a mass of 1,500 kilograms, and let's say the normal force that we measure acting on these front wheels to keep the car propped up, because it's not falling, is 7 kilonewtons. Now, if you're not used to kilonewtons, well, 1 kilonewton equals 1,000 newtons, so you can think of this as 7,000 newtons. So the force, the normal force on the front wheels is 7 kilonewtons. What is the normal force needed on the back set of wheels to keep the car in equilibrium? In other words, to keep the car from suddenly starting to fall. Right? Because that's probably what we do unless we had normal force on it. Well, let's treat our car like a bar. So if we drew a free body diagram, we would represent the car, instead of as a single point, like we were used to back in Unit 2, we're going to treat this as a rod, or as a single line. Okay, so this represents my car. This is my car's center of gravity. I don't know necessarily where it is, so I just know it's probably going to be somewhere between the rear wheels and the front wheels. So I just marked that there. Now, the first force that we know is acting on this car is the force due to gravity. So I'm going to write mg. And I need to put forces in a certain position when we're dealing with equilibrium problems. One key fact to note is that the force due to gravity is always placed at the center of gravity of the object. So let's make a big note that gravitational force always acts at the center of gravity. That's a huge understanding that you need to have. And when you go to my concept questions tomorrow in class, or the next day in class, I'm going to be asking you about that, so you need to know that. All right. Well, we know that m times g is 1,500 times 9.8. So we can say that the weight of this car, the gravitational force of this car, acting on this car is 14.7 kilonewtons. Why did I put it in kilonewtons? Well, right now it's an easier unit to deal with, so I don't have to write as many zeros. And with an equilibrium problem, as long as I'm keeping all of my forces in the same units and all of my distances in the same units, things will work out. And we don't need to worry about converting it to meters and newtons. As long as all of my forces have the same units, all of my masses have the same units, and all of my distances have the same units. I think I just forgot to mention mass there, but that's also true. Okay. Our next force is the normal force acting on the front wheels. And that force is 7 kilonewtons, and we're going to say it's acting at the very front of the car, or the front of our little diagram over here, way off to the right. We also know that we have a normal force acting on the rear wheels. We just don't know what that value is. We're being asked to calculate that. So how do I find out what this normal force is? Well, let's use one of the facts of this car being in equilibrium, and that is that the sum of the forces is equal to 0. Now remember, I have to keep an account in each of my two directions, x and y. So I have to figure out what all my forces are in the x direction and add up all the forces in the x direction to set them equal to 0. And then I have to do the same thing in the y direction. Well, this one's easy because there are no forces acting in the x direction. So I don't even, in this particular problem, I don't need to deal with the x direction. I can go right over here to the y direction. So let's do that. So I have two forces. I just went left to right. So I add up all the forces, the normal force on the back wheels, minus 14.7 kilonewtons because this is pointing down. That's negative. And plus 7 kilonewtons. And because on the right-hand side of my equation, I have to have the sum of the forces equals 0, I have to put 0 on the right-hand side of my equation. Well, this is an equation we can solve for the normal force. So let's do that. Let's add our like terms. And then we solve, and it's pretty easy to see that the force, normal force on the back wheels has to equal 7.7 kilonewtons. Okay, let's go to a related example. Let's say now I'm being asked for how far the center of gravity on the car is from the back. We certainly know that the center of gravity is going to be somewhere between the rear wheels and the front wheels, but where along that is the center of gravity? We have to figure that out. Well, I hope I don't run out of voice before the end of this video. Let's use another fact, our fact number 2, to see if that will help us. Let's set, actually I need to change that to 2.5, the distance between the wheels. I forgot to do that. Okay, let's set up our free body diagram. Now you probably don't need to do this in your notes because you have this in example number 1. Well, maybe it still is useful. But this is the same free body diagram we had in problem number 1. And of course now we know that this is 7.7 kilonewtons. I know that this is a distance L from the rear wheels. I don't know what it is. That's what I'm being asked for. So I'm going to label that. And if this is L, then my distance from my center of gravity over to the other side has to equal this number minus L. So that distance is going to be 2.5 minus L. Okay. Well, let's use the fact that when our car is in equilibrium, the sum of the torques is equal to 0. So I have to make an account of what each of these torques is. So let's label one of them. Oh, well, let's not forget that torque is equal to R times F times sine theta. Now let's label each of these torques. This is going to be torque 1, this is going to be torque 2, and this is going to be torque 3. So I'm just working from left to right on my diagram. Now, in this particular problem, I am going to use the center of gravity as a pivot point. I could have used any other point. I could have used this point or that point. As a matter of fact, it might have made sense if I use this point over here, but I'm going to use the center of gravity because sometimes you need to actually know how something is rotating around its center of gravity. So let's use the center of gravity as a pivot point. All right. Well, now that that's established that this is our pivot point, let's find what torque 1 is. That is going to equal the distance from the pivot, which is L, times the force itself, which is 7.7. And since these two form a 90-degree angle, then I just have sine of 90. Now I have to ask myself, is this a positive or a negative torque? Remember that counterclockwise is positive. Well, if this were the only force acting on this car and it's pivoting around this point, well, this is going to want to push it in a clockwise direction. So this torque that I just put down here actually has to be negative. So my first torque, when I simplify this, is equal to negative 7.7 times L. Torque 2 we can treat in a similar manner. We have 0 because it's at a distance 0 from the pivot point, times 14.7 times sine of 90 degrees. Well, all of that equals 0. So what I've done is I've actually, this force, the weight of the car, contributes no torque to the system. Now let's figure out what torque 3 is. When we do that, we have 2.5 minus L because that's our radius R from the pivot. The force is 7 kilonewtons, and again, sine of theta is 90. That's exactly what I plugged in here. R times force times sine of 90 degrees. And what I have is an expression 2.5 minus L in parentheses times 7. And then I can use the distributive property to distribute, and I end up with this expression for the torque due to this force right here. Okay, well, my formula tells me that the sum of all these torques, 1, 2, 3, those 3 torques added together, have to equal 0. So this is torque number 1. This is torque number 2. This is torque number 3. Those two terms put together. And all those have to equal 0. So now I have an equation that I can solve for L. Let's collect our like terms. Combine our like terms. And I get this equation. And then when I solve that equation for L, I get 1.19 meters. Okay, so it's telling me that the center of gravity is located 1.19 meters away from the rear tires. Well, that's kind of interesting if you think about it, because it wasn't 2.5 divided by 2. It's not halfway between these two. It actually ended up a little bit closer to the rear tires than it did to the front. So center of gravity or center of mass doesn't necessarily need to be halfway in between the two ends of an object. Okay, now that's it for advanced. So you guys, if you want to stick around, it's optional. AP, you need to take notes on another example here. It's going to get a little more complex and hairy, but that also makes it more fun. So let's look at a third example for AP here. So we have a hero, superhero, Batman or Robin or something like that, and this person has a grappling hook hooked up to a window, and they're trying to climb up to get into this window right here. And we have a pretty complicated system. We have this person slanting at an angle, and the rope is at an angle. So life is going to become very interesting for us. So our job is to be able to identify and calculate all the forces acting on our hero here. So let's represent our hero in our free body diagram by a straight line. It's tilted. And as a matter of fact, it's tilted at a 60-degree angle with respect to the wall. I wonder if I misidentified that angle. No, that's the right angle. Yeah, that's right. 60 degrees. Okay, which means that, of course, that other angle has to be 30 degrees, so we might as well go ahead and identify that. I'm going to assume that the center of gravity for our hero is halfway between his feet and his head. So I'm going to place it at a distance of 0.85 meters, which is half of his height. And then I'm going to draw my first force, which is his weight of 700 newtons. And of course, we know it acts at the center of gravity, like I explained in example 1. Then we have a tension force on the rope. And now the interesting thing about the tension is that it's acting not at our superhero's head or at his waist or at his feet. It's at a distance of 1.3 meters, because I specified that in the previous slide. So his arms are a distance of 1.3 meters above his feet, and that's where we're going to put our tension force. Now this is starting to get a little bit of a messy diagram here, so I'm actually going to draw a second diagram over here because I need to label some angles. We know that this angle is 30 degrees between his body and horizontal. And we also know that this angle, because it's alternate interior angles, has to be 30 degrees. There's a little bit of foreshadowing. You probably didn't know you needed to know that yet, but you'll find out you do. And then this angle right here between vertical and our rope is 20 degrees. Okay, so that's just the same diagram as right over here. I'm just making the little things a little easier to label. Okay, well, we also have a normal force acting on our hero because he's leaning against the wall. So that wall has to be pressing perpendicular to the surface, so we have a normal force. We don't know what it is. And we're also going to assume that there's some friction here because one could imagine if there wasn't any friction, these feet would just slide up or slide down. So we're going to assume that there's some friction force. We don't know if it's acting up or down, but let's assume that it's acting up. And then if it ends up acting down, we'll just get a negative sign for our force due to friction. Excuse me. All right, so I've identified all the forces. Now I need to actually calculate them. Well, let's use our two facts of equilibrium. Turns out to be 3 equations. The sum of my forces in the x direction has to equal 0. Sum of my forces in the y direction has to equal 0. And the sum of the torques has to equal 0. Well, there are 4 different forces to keep account of. So I'm going to always just work from left to right. I see that this normal force is acting in the x direction, so I'm going to write that down. And then I also have a component of this force acting in the x direction. So I better have minus f of t. Now I put minus because I figured that the x component is going to be going in the negative direction toward the left. And then I have to, since I have to take the x component of this, well, I know that this angle from here to here is 20 degrees, which means if I want the x component, that I better take the opposite of this angle, okay, opposite of our hypotenuse. So I'm actually going to put sine of 20 degrees. So normal force minus tension times sine of 20 degrees is equal to 0. Now let's make an account of everything that is in the y direction for forces. So I have the friction force. Let's write that down. I have the force due to gravity, so let's write 700 newtons. And then I have the y component of this force right here. So that is going to be tension force times cosine of 20 degrees. And all of that equals 0. Okay, now before I go into figuring out what the sum of the torques is, I want to help myself as much as possible here. Now remember in my slide when I talked about this, I said if you don't have a pivot point defined for you, you can pick the pivot point, okay? It would be very unwise for us to pick the center of gravity as a pivot point in this problem. The reason being is that we have two unknown forces way out here, and if I don't put my pivot point here, those have to contribute a torque which I have to figure out. And now I have a messy system of equations, and I will be a very unhappy camper. So instead of picking the center of gravity as the pivot point, I am going to pick our hero's feet as the pivot point. So let's use the feet as the pivot point. Why? Because if I start to calculate torques, let's calculate the torque due to this force. Well, it's going to end up to being 0 times Fn because the distance from the pivot is 0. Okay, so what I've essentially said is that if I put the pivot point here, all of the forces acting on this point are going to equal 0. Which means that this torque is going to equal 0. The torque due to that force. And we can also say that the torque due to this force is equal to 0 because we wisely put our pivot point right here. That means that this one is going to produce a torque, but it's going to be relatively easy to calculate. I put a negative sign here because it is going to exert a torque that is going to want to move this thing in a clockwise direction, which is negative. So that's negative 0.85 because this is our distance, r, times the force itself, 700 newtons. And now I have to be cognizant of the fact that now my angle theta is not with respect to vertical or horizontal. It's with respect to my radius, which is going in this direction. Okay, so now let's see if I actually, I did this correctly. Okay, so this angle right here is the angle I'd be interested in right here, between here and here. Okay. Now that angle, because this line and this line are parallel, this angle also has to be 60 degrees because this angle is 60 degrees, which is why I wrote sine of 60 degrees in there. Okay. And when I evaluate that, excuse me again, when I evaluate this, I get negative 515. And then finally, let's calculate the torque due to this force, the tension force. So I have a distance of 1.3 meters. The force is Ft. I don't know what that is, so I have to calculate that. And then I'm going to have sine of some angle. I don't know what that angle is, but I can calculate it because over here in this diagram, remember it's the angle between the force and the radius. Okay, and the radius goes along our object here. So I could have picked this angle from here to here, or I can pick this angle from here to here. I'm going to pick this angle from here to here because it just involves me adding 30 degrees plus 90 degrees plus 20 degrees. Well, 30 plus 90 plus 20 is equal to 140 degrees. Now, before I get a little out of hand here, if you're taking, of course you're taking notes, but this is the angle that I calculated, and I found that this angle is 140 degrees right here. Okay. All right. So when I simplify this, I evaluate 1.3 times sine 140 degrees. I get 0.836 times f of t. Now, before I go to my next step, let's make sure that this really is a positive torque. So if I imagine that this is the only torque acting on the system, it's going to want to push things in this direction so that it will rotate in a counterclockwise direction. and that is a positive torque, so this sign out in front is going to remain positive. Okay, I figured out all the torques on my system. Now let's use our equilibrium equation, that the sum of all the torques equals 0. Let's add up all the torques together. I have 0 plus 0 minus 515 plus 0.836 times f of t. And on the right-hand side of our equation, that has to be set equal to 0. So now I have an equation that only involves one variable, f of t, the tension force. And when you solve for that, you find out the tension force is 616 newtons. Great, we've just calculated one of our unknown forces. Well, we can calculate our other two unknown forces because each of these other two equations only involves f of t and one unknown. So over here, if I plug in my tension force here and solve, I'd get a friction force of 121 newtons. And if I do likewise over here in this equation, I'm going to get a normal force of 210 newtons. So we've calculated all of the unknown forces, and we've identified them. All right, so that's equilibrium at an AP level. It can get messy, but you're capable of keeping those things sorted. We're going to have an opportunity during class tomorrow to do some group work on this. I'll give you a couple of problems. Since these are pretty long and involved, I'm not going to give you too many. All right, so that's it. I think my voice is about ready to quit on me, so I better stop talking, and I look forward to seeing you soon. Bye.